So the problem that we're given here is the following. It says, in the following problems, and this is just part A that we're looking at, substitute e to the mx into the differential equation and determine all the values of m for which e to the mx is a solution of the equation. And this kind of highlights what's special about differential equations. A differential equation involves functions and their derivatives. And the solutions to a differential equation are not numbers, they're actual functions. And what I mean by that is the solution to a differential equation could be y equals sine 2x, or it could be y equals ln 5x, or it could be something like e to the x squared. That might be the solution. So we're actually looking for an actual function. And there may be many functions that satisfy any given differential equation. So just as we begin, I just want to highlight that this is the notation for the second derivative. So that's really equivalent to d2y by dx squared. This is, of course, the first derivative. This is dy by dx. And finally, we've got minus 2y. And we need that to be equal to 0. So at the end of the day, we would normally, if we were handed this equation, be looking for a function, any function, such that its second derivative added to its first derivative, subtract twice the original function, gives 0. Well, the nice thing is you don't have to solve that. We're not asking you to solve that. What we're asking you to do is look at y equals e to the mx and say, yes, that can be a solution, except for only particular values of m. And what's understood here is that m is a constant. Okay, so it's not a variable in this case. It's not like x or y. It's a constant. So this could be e to the 7x or e to the pi x. It could be something like that. It needs to be a constant. So first and foremost, we'll say, okay, y is equal to e to the mx. We need the two derivatives. So the first derivative, dy by dx, is m e to the mx. And you would get that from first year calculus, where you're taking the derivative of an exponential function. It's e to the mx again, but then you must differentiate the exponent. So mx differentiates to give m. The second derivative, d2y by dx squared, will be m times the derivative of the e to the mx again. Well, the e to the mx, once again, is m e to the mx. And so now what do we have? We have m squared e to the mx. All right, so these three expressions we will insert into this equation with the hope that we can find m values that make the equation true. So I'm going to place the second derivative, which is m squared e to the mx, in for the second derivative, and to that we're adding the first derivative, m e to the mx, and then finally minus 2 times the original function, which is e to the mx, equaling 0. And this is what we're trying to solve. This is the equation that we're trying to find values of m that will satisfy it. Okay, so with that said, let's do this. Let's look at this and say to ourselves, well, e to the mx is common across all three of these terms. So I will factor that out, and I've got e to the mx. Left behind would be an m squared plus an m minus 2, and that has to be equal to 0. Well, I look at this structure and say, oh, well, that's a simple trinomial that needs to be factored. So I'll say e to the mx multiplied by m plus 2, m minus 1 equals 0. So now we just have to solve that equation, and that's actually quite easy to solve. We look at first maybe these two factors. In fact, we'll look at all three of them at once. I'm not going to separate them. We have e to the mx, which could take on the value of 0 to make this 0. We have m plus 2. That would need to take on a value of 0 to make this 0, or m minus 1 equaling 0. Well, these are trivial. These two are trivial. That's m equals 1, and this is m equals negative 2. Now this one here, e to the mx, if you just think back to the graph of e to the x, in general, all e to the x's are asymptotic. They're asymptotic regardless of this exponent. They're asymptotic to the x-axis. So they look something like this when you graph them. They come up and do something like this. And so in fact, there is no point where e to the mx ever reaches a value of 0. So there's no solution here. So our only solutions are m equals negative 2 and m equals positive 1. All right. Now that's where the question finishes. You're actually done at this point. But I never mind going back and just having a little check. I want to make sure that in fact this does satisfy the equation, and this does. So what I will do is I'll verify the m equals negative 2 solution, and you can do this on your own. You can do the m equals 1. So let's do that little check now. So we'll check m equals negative 2. So that means that y would be equal to e to the negative 2x, and then the first derivative of that, y prime, would be negative 2e to the negative 2x, and the second derivative is going to be positive 4e to the negative 2x. Well, now if we insert those three expressions back into the original equation, y double prime plus y prime minus 2y, we get the following. We get that y double prime 4e to the negative 2x plus y prime, so that's plus negative 2e to the negative 2x minus 2 times y, 2e to the negative 2x. Where are we at now? We've got 4e to the negative 2x, and this works out to minus 4e to the negative 2x, and so that's going to work out to 0. And so it does check out. It's consistent with the solution we got. Now, I would encourage you to go back and check m equals positive 1, because that was our other solution, and verify for yourself that this still holds up. Now you might say, well, what if we tried, m equals some other number? And I would say to you, sure, let's check it out and just confirm that if we pick another value for m, we're not going to find something that satisfies that equation. So let's just, we know this is going to be wrong, or it should be wrong, but we're going to check something simple like m equals 3. So that means y would be e to the 3x, y prime would be 3e to the 3x, and then finally y double prime would be 9e to the 3x. Well, now if we examine y double prime plus y prime minus 2y, what do we get? We get 9e to the 3x plus 3e to the 3x minus 2e to the 3x, which nets out to be 10e to the 3x, which clearly is non-zero. That's not equal to 0. So therefore, m could not be the value 3. And in fact, if you went back and tried any other value, you'd find that the only solutions lie with m equaling 1 or m equaling negative 2. So just in a nutshell, I just want to highlight one more thing for you here. It's the fact that when you are solving differential equations, whenever you're solving differential equations, the solutions themselves are functions. So they are functions. You can see that the solution to this differential equation is either y equals e to the negative 2x or y equals e to the 1x or e to the x. Hopefully that clarifies how you attack that kind of question.